Hello, I'm Lina Gopos, majoring in electrical engineering. I'm a member of the solar car team, and I'm in charge of all the protection in our project.
Hello, my name is Usman Khan. I'm majoring in computer engineering. My jobs in this project have been designing the rectifier circuit and laying out PCBs for manufacturing.
Hello, my name is Mark Durhake and I am responsible for the design of the inverter stage and control circuitry.
Hey, my name is James Jones and I'm majoring in electrical engineering. I helped to design the magnetic components of the circuit, did the 3D modeling, and managed the project schedule.
The essence of our projects come from the fact that most of us are members of the SIUE solar car team. Last year, our team decided to upgrade the solar car from a single occupant to a multiple occupant vehicle for the American Solar Car Challenge. Due to this decision, the energy of the battery as well as the amount of power needed to charge it also increased. This is the problem we wanted to solve. Our solution was a switch mode power supply. This circuit will sit between the AC inputs and the car battery to charge it whenever solar energy is not available. A power supply comes in many forms. It can be unregulated or linear regulated. In our case, we are using a switch mode power supply, which uses switching devices that are turned on and off at high frequency to convert power. That power is stored in components such as capacitor and inductor to supply it to the load. Our switch mode power supply will take an AC power from a NEMA 1450 outlet, convert it into a DC power, and supply it to the battery pack of the car. This level is referred to as the level 2 charging system that takes an input between 208 and 240 volt AC at a max of 40 amp and will supply up to 10 kilowatt to the battery pack. The physical connection between the input and the charger circuit will be made by using a J1772 connector.
As the table on screen shows, the power supply will take in 240 volts AC at up to 40 amps at the input. The output will be 300 volts DC at up to 30 amps.
Here is the block diagram of our project showing the flow of information and power in the circuit. The first block is the J1772 connector that will plug into the NEMA 1450 outlet and will communicate with the control board about the state of charge of the battery. The AC power that will come out of the J1772 will pass through an EMI filter to reduce the noise. Then it will be converted into a DC power by going through a rectifier. The DC power will go through an inverter that will produce a modified sine wave which will go through a step-up transformer to provide isolation from other stages of the circuit. Finally, the power will be fed to our load through a rectifier and output filter. The control board will also communicate with the inverter stage to switch the MOSFET and change the output power. Due to the COVID-19 outbreak and the stay-at-home order, it was difficult to continue proper testing and ordering parts to finish the final circuit. Although a final circuit of the 240 volt system was not able to be completed, a lower power 120 volt system prototype was successfully developed and tested. This 120 volt system prototype is what we are going to discuss within this presentation.
The block diagram before showed the three major chunks that the circuit is split into. The first block we'll discuss is the input board block. This houses the AC input, EMI filter, soft start, and rectifier. The circuit will use a J1772 interface to connect to an EV charging station. These are called EVSEs, electric vehicle supply equipment, and they serve to talk to the vehicle and let it know how much power is available and if the process should stop given a fault condition. To achieve this functionality, the J1772 connector uses 3 larger power pins and 2 smaller signal pins. One of the signals is called proximity detection, and it just indicates to both the vehicle and the EVSE that the charger is plugged in. The other signal is a plus-minus 12 volt PWM signal called the control pilot. This signal will communicate the state of charge using the positive voltage level and the available current through the duty cycle. The control circuitry will take the signal and use this information in the control loop to determine how much power to push through the inverter. This functionality would be necessary if the vehicle was to charge from a standard EV charging station.
Most electronic devices contain an EMI filter in order to reduce the high-frequency electronic noise that travels along the electrical conductor through the air or radio wave, which may cause interference with other devices. The topology that we are using for the EMI filter is a LC circuit. The inductor, common mode chuck, is rated for 200 microhenry at 100 kHz. It allows low-frequency current to pass through while blocking harmful high-frequency currents. The capacitor provides a low impedance path to reroute the high-frequency noise away from the input of the filter to the ground connection.
To convert our AC power into DC power, we'll be using a standard full-bridge rectifier. This topology isn't the best if power factor or efficiency are concerned, but the alternatives were ruled out due to changes in the project and difficulty. The last part of our input board is the soft start circuit. This is simply a power resistor and a place for a contactor or relay to attach to.
To begin our discussion of the inverter stage of the project, we will take a look at the picture shown on screen now. This circuit is known as a full-bridge converter, or more simply known as an H-bridge. Great consideration was given to what converter topology would be best fit for the specifications of this project. Topologies such as flyback converters, half-bridge converters were considered, along with even more novel solutions such as matrix converters to actively control the power factor of the circuit without the need for a DC stage. Though ultimately, the full-bridge converter was chosen for the advantages it presented for its higher power density and simplicity of design. With the topology selected, various methods of control were then explored. That is to say that there are various ways in which the generalized circuit presented may be implemented to achieve different desirable design outcomes. Some examples of different implementations are as follows: voltage-fed converter, current-fed converter, or resonant converter. Each design presented has different advantages and disadvantages to them, along with various means by which they can be controlled, meaning things such as voltage mode control, peak current mode control, or average output current control. For example, a voltage mode voltage-fed converter sees the bridge fed by a capacitor, while the output voltage is monitored and used to control the on-time of the converter. A converter of this sort works as follows. In order to invert the DC voltage generated by the rectifier, pairs of diagonally connected switches open simultaneously to draw current through the primary of the transformer, meaning that MOSFETs M1 and M2 open to draw current in one direction through the primary, and then after a period of time, M3 and M4 open up in order to draw current in the other direction. The simplicity of this design allows for quick implementation. However, it is subject to power losses during the turn-on and turn-off times of the MOSFETs. It can also present poor regulation against load or line changes during operation. So instead, a peak current mode current-fed converter might be explored. Unlike a voltage-fed converter, which uses a capacitor to feed the H-bridge, a current source is used instead. This means that all legs of the bridge must be on at all times to prevent voltage spikes from harming the circuit. By having current mode control, the voltage may be monitored along with the peak value of current through the inductor. By monitoring the current as well, the circuit gains added protection against sudden changes in operation. These options, and the others that were previously mentioned, were considered, and it was decided that because the team required a constant current charger to charge the battery, whose voltage would fluctuate as it charged, a Hall effect sensor would be used to monitor the current to the battery, and a voltage-fed converter would be sufficient to regulate said current. With a full converter circuit decided on, let us now consider how to actually drive it. An Arduino Uno is used to produce two 5-volt 50 kHz square waves, each offset by 180 degrees. These two waveforms are then used to turn the diagonal switches of the converter on in order to invert the DC voltage present on the bridge. Now, in order to turn a MOSFET on, the voltage between the gate and the source of the FET must exceed the MOSFET's threshold voltage. This may vary between devices, but for power FETs, 15 volts will turn on the MOSFET completely. In order to amplify the 5-volt signals coming from the Arduino, a device known as a gate driver is used. These are ICs that are designed to help drive the gate of a MOSFET by allowing a change in logic level between the input and output signal, as well as supplying more current for the turn on and turn off of the MOSFET. The gate drivers used in this project are isolated as well, to keep the low voltage control circuitry separate from the high voltage present on the H-bridge. The picture shown on screen now is an example of what each gate driver does. Something to note is the difference between the lower two driver circuits and the upper two. Recalling that 15 volts will turn each MOSFET on, it's a simple task to turn on the lower two FETs because both of their sources are always connected to ground. When the upper two MOSFETs turn on, however, the source of each of those will float near the DC voltage of the bridge due to the low on resistance of each FET. Thus, a technique known as high-side driving is employed. Using what is known as a bootstrap circuit, consisting of a bootstrap diode and capacitor, the gates of the upper two FETs can be turned on. The circuit works by initially charging the bootstrap capacitor up to 15 volts. The capacitor will now act as the source of voltage for the gate driver. Once a signal is applied to the driver, charge will be depleted off of the capacitor to charge the gate of the MOSFET. Notice that the driver circuit is not connected to ground, but rather is referenced to the source of the FET. This is done so that the gate-to-source voltage of the MOSFET may be brought to 15 volts, while allowing the driver circuit to float above ground, meaning that once 15 volts is applied to the gate, the MOSFET will turn on and the source will be pulled towards VDD. As the source rises, the driver circuit will also rise in voltage reference to ground. For example, if the source is at 100 volts, then the gate will be at 115 volts reference to ground, but only 15 volts reference to the source of the FET. Now this is why the bootstrap diode is needed to prevent the high voltage present on the gate from damaging the 15 volt supply. Just like the selection of the converter type, the design of the driver circuit was given much attention. It was important to turn on and off each MOSFET as quickly as possible to minimize switching losses. Initially, a simple resistor network was used to limit current out of each gate driver to prevent damage while still allowing for fast switching intervals. Due to lower levels of parasitic capacitance and inductance present on a PCB, each waveform appeared acceptable. However, breadboard tests showed flaws in said design once other implementations were explored. In order to solve the fast switching issue whilst drawing little current from the gate driver, larger external BJTs were added. Shown here is the resistor network signal on the gate of one of the MOSFETs on a breadboard. Shown here is the improved circuit. It can be seen even on the breadboard. The second circuit provides considerably improved switching times. On the prototype circuit, the first design is used because the second was created afterwards. In addition to this, 15-volt Zener diodes were added to the gates to help prevent overvoltages from damaging them. Pull-down resistors were also added to help ensure that the circuit is off, and Schottky diodes were added to help protect against reverse voltages. With the driver circuit explained, let's now take a look at an example waveform. This waveform is the voltage across the primary of the transformer during operation. It can be seen that the signal has positive and negative peaks at 50 kHz, meaning that proper inversion is occurring.
One of the biggest reasons that we need a transformer in our circuit is to galvanically isolate the circuit. This basically means that we will be separating our input circuit from our output circuit to eliminate stray currents and differences in ground potential. The high frequency of the signal allows us to use a power transformer that is much smaller than if we were to use a 60 Hz signal. The transformer itself has to be specifically designed to fit our needs. For this purpose, we chose an EI ferrite transformer core. Ferrite is a ceramic material commonly used in high-frequency magnetic component design and performs better at high frequency when compared to typical iron cores. The core we have specifically chosen is the 3C95E100. We chose this core because it has a high working temperature range. This means that we will get minimal power losses as the temperature of the core rises. This is especially important when considering that the circuit will be producing a large amount of heat and the fact that the solar car will be racing in places such as Texas. Using this EI core configuration will also make it easy to create an air gap within the core of the transformer. It is important to have this air gap because it will increase the size of the hysteresis loop of the transformer. This basically means that we can push more power through the core without having to worry about core saturation. Shown here is a 3D model of what the transformer will look like. The bobbin for this transformer has to be designed and 3D printed. For reference, this is the brown object that can be seen in the transformer core. The transformer will be a step-up transformer with a ratio of 1 to 1.3. This step-up will increase the input voltage from 340 volts to about 400 volts. We will be hand winding the bobbin with a Litz wire. Litz wire is multi-stranded wire that will help to reduce the skin effect as well as reduce overall power losses in the transformer. Between each layer of the wiring will be a thin layer of insulation tape. This is done to create layers of protection between each loop of wire from things such as short-circuiting and sparking. It is important to note that the secondary side of the transformer will be center tapped. Center tapping helps to reduce ringing in the output, as well as further reduces the power losses of the transformer. So, as mentioned before, by center tapping the transformer, we can reduce the power losses. Center tapping the transformer also allows us to only have to use 2 diodes for the output rectifier. Schottky diodes, which are a type of fast-switching diodes, will be used for this rectification stage. The rectifier will turn the high-frequency AC waveform that it receives back into a DC waveform. After the rectifier, we'll be using an output choke to smooth out the current. On the output, we will also be using an ADC to monitor the output voltage and a current transformer to monitor the output current. These 2 values will then be sent back to the microcontroller, which will modulate the H-bridge based on their values.
Next, we'll move on to the control circuitry. As was mentioned earlier, the control circuit uses a Hall effect sensor to sense the output current. This device is also isolated, allowing for complete isolation of the control circuitry. It works by returning a linearly ramping voltage between 0.58 volts and 5 volts in 90 millivolt steps. This return voltage is read in by the Arduino, and a PID is used to adjust the pulse width of the signals sent to the MOSFETs. This is how the circuit is able to control the output current.
For the testing of the boards, since all the interesting parts of a power supply are invisible, we need a couple of devices to analyze the behavior of the circuit as it operates. This includes an oscilloscope, multimeter, and current clamp. Along with this, we need a power source and a large resistive load to test on. Since controlling the power output is the goal, the tests are done on a resistive load. The inverter test will include increasing the power to the resistive load to test the range of the circuit. We'll use a large resistive space heater for testing anything above 100 watts. This was for both power boards. The major part to test on the input board was the rectifier. We shorted across the common mode choke of the EMI filter and removed the capacitors to test the rectifier independently. The fuses were left in for safety reasons. We wired the load for a power draw of a little over 1 kilowatt and then plugged our circuit into a 120 volt outlet. Whoa, that's immediately heating up.
Yeah, it's 4 amps.
Cool. Look at that.
So that works.
Didn't blow?
Nothing blew up this time, and we were able to successfully push a kilowatt through.
Shown on screen now is a waveform of the circuit on startup, operating at around 50 watts. Though as was mentioned earlier in the video, multiple kilowatts are desired out of the circuit. The prototype of the full circuit is designed to handle 1 kilowatt. As such, shown on screen now, is the output operating at 1 kilowatt. There are various things to note about this. Firstly, that the waveform is indicative of the need of a custom-designed output inductor. Second is the need for snubber circuitry across all power silicon elements in the circuit to help protect each device from damage. Lastly is the need to speed up the control circuit's operation to help regulate against mains input frequency. Shown now is the current waveform read by the Arduino through the Hall effect sensor. Here it can be seen that the circuit is regulating the output current.
So, as can probably be guessed, this project has a hefty budget and bill of materials. This comes from the fact that high-power components are expensive, especially when trying to keep them small. The breadboarded prototype had some major costs, such as the input transformer, capacitor, load resistor, and transformer core, with the total cost being $209. The 120-volt PCBs were even more expensive, needing components like a contactor, transistors, diodes, and gate drivers. The total cost for these PCBs came out to about $396. The final circuit dwarfs both of these, however, needing components like its bulk capacitor, power MOSFETs, ferrite cores, and heat sinks. The cost for us to build and test the final circuit will cost a staggering $1,109. These costs do, however, take into consideration the testing phase of the project. So if we were to build it and everything worked on the first try, it would cost a bit less, at around $800. If we were to scale up production, this price would further reduce, since buying bulk parts is cheaper than buying singles.
On a personal and social level, this project has helped me build a strong team of mindset. Being within a semester to embrace the workforce, I've learned how to work and communicate effectively with people with different perspectives than mine. Engineering-wise, the hands-on experience has really helped me realized that simulation and real-life testing can be very different. This project has taught me a lot of subjects that I didn't know about. It has taught me how to learn on my own and research many different engineering aspects.
I think I learned a lot of important things throughout this project. Constantly having to research and double check myself, teaching myself how to properly design components, and really having to be on top of my time management, just to name a few of them. Watching everything come together and having a portion of the circuit work properly is really rewarding as well. Overall, I'm glad to have been part of this project and this team.
This project was definitely difficult. I've had to research and learn about topics that were not only new to me, but also very complex. However, in all that, I've learned a lot, not only about electrical design, but also how to do a proper engineering design project. It takes a lot of energy and coordination to make the effort of many people come together, and I feel like I've become better at that. In terms of engineering, this project gave me a reason to research aspects of electrical design that I was not familiar with and did not have the chance to research. I feel as if these two aspects were very valuable, and I hope that future projects are benefited from this new experience.
Thanks to this project, I was able to learn more about electrical design on my own than what I ever thought possible. I came to trust my own instincts when it came to the design process and learned how to lead better. To give an example, there can be circumstances where consistent continued negligence or incompetence can occur, which results in substantial setbacks out of your control. During such events, it's not only important to continue planning for the future, but also to keep up team morale, as well as to continue to pester the source of the problem so that the project might be able to move along.
If this project were to be continued, the charging system would be upgraded to a high-power 240-volt system. This upgrade will entail components rated for the higher power as compared to the 120-volt system. The charger will use the J1772 connector at the input. To improve the efficiency, we can correct the power factor and the zero voltage switching of the circuit. Lastly, we could 3D print an enclosure for the circuit so it could be easily mounted to the car. We would like to express our deepest gratitude to the School of Engineering for the financial assistance provided for our project. This project would not have been possible without the help and support of many people. To start, we would like to thank our solar car team advisor, Dr. Andy Lozarski, for his valuable advice on the EMI filter design, Steve Muren for helping us get the parts needed for the project, and Dan Hauer for his constructive criticism. To Mike Bassler and Randy Hamilton for their insight on the design of the full bridge converter and the digital control loop. To Dr. Bradley Noble for the PCB design. And I'm personally thankful for my teammates and all the hard work they have put into this project. Thank you for watching.